All right, so thank you for doing that. All right, so back to sequences. So a recurrence relation for a sequence is an expression that describes an in terms of a1, a2, a3, up through an minus 1. And it may not include all of these terms. It may not include any of these terms. But you can't describe an in terms of an or an plus 1 and so on. It's got to be prior terms in the sequence. And if there is a recurrence relation, right, the sequence that that relation corresponds to is called a solution for the recurrence relation. So for example, we could have a recurrence relation an equals twice times an minus 1. And we also specify a1 equals 5. And so a solution to this recurrence relation would be the sequence 5. And then a2 is just twice a1, which is 10. a3 is twice a2, which is 20, 40, 80, and so on. So there's a sequence that solves that particular recurrence relation. So what about this relation? a1 equals 1 and an equals n times an minus 1. What do the terms of that sequence look like? I'll start you. There's the first term. So what's a2? 2 times a1 is 2. What's a3? 6. What's a4? What is it? 4 times an minus 1. 4 times 6, 24. And then a5 is 5 times a4 is 120. So what does an equal to in general? N factorial. So there's a recurrence relation for factorials. How about a1 equals 5, an equals 5 plus an minus 1. So the first term is 5. What's the next term? 10. 5 plus the first term. What's the third term? So you got the pattern. So what's the formula here? Just 5 times n.
Is that n greater than 1 necessary? Because you can't really go below your starting value.
If you don't have the n bigger than 1, technically I'm saying something that's not always well defined, because this also says a1 equals 5 plus a0, and we haven't defined what a0 is, except that a0 would be 5 plus an minus 1, which is a minus 1. So yeah, we want that n bigger than 1 there. So how about an is n plus an minus 1. a1 is 1. So first term is 1. What's the second term? a2. 3. What's A3? 3 plus 3 is 6. What's A4? 10. A5. So these are the so-called triangular numbers, because each of them corresponds to the number of points in a triangle drawn like this. So if you go up to here, there's 1. If you go all the way down to here, there's 3. If you go down to here, there's 6. If you go down through this whole triangle, there's going to be 15, and so on. And the formula for this, anybody know this? N times n plus 1 over 2, good. So that's a general formula for triangle numbers. So all kinds of different ways that we can take recurrence relations and come up with sequences corresponding to different formulas. And it's kind of interesting because here we're doing addition and our solution is multiplicative. Here we're doing multiplication and our solution has a factorial. Here we're also doing addition, but our solution actually has a square in it, n squared plus n over 2. And so there's some back and forth between what's going on in the sequence, what's going on in the solution of the recurrence relation. And these things, expressions like this, where we have some sort of base case and we have some expression of the nth term in terms of prior terms, recurrence relations, we're going to encounter these a lot starting later on this week and all of next week. This is going to tie right into mathematical induction, which is where we're heading with all of this. So here's a famous recurrence relation. A1 is 1, A2 is 1, and for n bigger than or equal to 3, AN is AN minus 1 plus AN minus 2. It's the sum of the two previous terms in the sequence. So this looks like 1 and 1 for your first two terms. The third term is the sum of the first two terms, which is a 2. The fourth term will be the sum of terms 3 and 2, so 1 plus 2 is 3. The next term will be the sum of 2 and 3, is 5. The next term is 3 plus 5 is 8, and then 5 plus 8 is 13, 21, 34, 55, and so on. So what's that sequence called? Fibonacci. We'll come back to the Fibonacci sequence later in the course, and we'll see where it came from, which was related to the population of rabbits. And we'll talk some more about it. But Fibonacci sequence has some really cool properties to it. For example, if you take any number and you square it, and if you take the two numbers on either side and you multiply them, they're always within 1 of each other. In this case, the square was 1 smaller than the product of those two expressions. Here, if we take 2 and we square it, we get 4. If we take 1 times 3, we get 3. There, the square was 1 more than the product of the terms before and after. And this is always the case. And it's one of a whole slew of really cool properties inside this sequence. It's just filled with symmetries and surprises. There is an expression that we can write to find out what the nth term is equal to. I don't have it memorized, but we'll go through it later on. when we revisit this, but it has the square root of 5 in it. That's what I remember about it. It's a really weird expression. Here's a real world example, compound interest. So suppose you get 5% interest annually. And suppose you start with an initial principal. I'll start with 0 for no reason. P0 equals $1,000. And you're putting it into this fictitious bank that actually pays you to put money into the bank instead of charging you. And every year they're going to give you 5% back on however much money you have in your account. So after 1 year, you start with $1,000. After 1 year, you're going to have all the money you started with plus 5% more of what that balance was. Which, if we factor out that initial principal, it's just 1.05 times the initial balance. At the end of year 2, you're going to have everything that you had at the beginning of the year plus an extra 5%, which is 1.05 P1. But since P1 is 1.05 P0, this is actually 1.05 of 1.05 P0, which is 1.05 squared times your original principal. And we'll go 1 more year. So year 3, you've got year 2 balance plus 5%, which is 1.05 times P2. And since P2 is 1.05 squared P0, this is 1.05 cubed P0. And you can imagine a general solution now. Your principal after n years is 1.05 to the n times your original balance. This is why investment is a good thing, right? Because initially you put in $1,000, you get 50 bucks right after a year. After 30 years, this will be more interesting. I don't know if it's that much more interesting though. Let's see. So after 30 years, you've got 4.3 times your original principal. So if you started with $1,000, you got $4,300. Of course, if you started with $1 million, you've got $4.3 million now. Now, when I was a kid, banks were paying about 10% interest on savings accounts. So if I had invested and if they had locked in that interest rate after 30 years, I would have 17 times my original investment. That didn't happen, though. All right, so recurrence relations. All right, you got the idea? So I'll have some homeworks Thursday's upcoming homework set. I'll put some questions on there related to sequences and recurrence relations, but we'll revisit recurrence relations multiple times in this course. All right, we already talked about summations, right? Those things. We did nested summations. I at least mentioned them. Right, so you can evaluate this inner sum first, and that gives you a function of j, and then you can evaluate the outer sum as usual. So let's talk about change of index. Suppose you want the sum from j equals 5 to 7 of some function f of j. Well, this is going to expand out to f of 5 plus f of 6 plus f of 7. But sometimes it's easier to write summations from an index of 1 or maybe 0. So how could I write this summation as a summation where I goes from 1 to 3 instead of 5 to 7? But I want the same value of the sum. Yeah. So this is exactly the same as this. Because when I is 1, this will be f of 5. When I is 2, it'll be f of 6. When I is 3, it'll be f of 7, and that's where it stops. So by changing the variable inside into some expression, we can change the lower and upper indices on the summation itself. And remember, this choice of variable is completely arbitrary, right? This w or this I makes no difference. Okay, it's the variable in a for loop. You have for I equals 1 to 10. You could just as easily have said for j equals 1 to 10, as long as everywhere inside the for loop you use j instead of using I. That's all we're doing here. I'm told at some schools you lose points if you say for j equals 1 to 10, though. I had a student who lost points on an assignment. The teacher said that I is the traditional variable to use for outer for loops. Actually took off points. But mathematically, it's exactly the same thing. Yeah, this particular school has, I think, a 30-page style guide that students, CS students get. I tell you how to name your variables, how to indent, where to put curly braces, and you lose a lot of points if you violate the style guide. I'm not going to name it. I'll tell you offline. Yeah. Let's see. So let's go back to geometric sequence, but as a summation. So we'll write Sn as the sum from I equals 0 to n of some constant a times some constant r raised to the I. So this is basically a plus ar squared plus ar cubed all the way up to a times r to the n. And we can find a formula for this sum. Which looks like this. And it's a fun little exercise to try to come up with that formula. Basically take this sum and multiply it by r. So over here you get r times s sub n. And over here you get this exact same thing, except it starts with ar and it ends with ar to the n plus 1. And then just subtract and most of your terms go away. And you can solve for Sn over here and you get this nice little closed expression. But this is an example where we have a sequence going from 0 to n, and in that case we have a formula for the value of that summation. But if we wanted the sum from 5 to 15, we can't use this formula. But we could modify this piece of our expression and then change our index from 0 to 10 instead of 5 to 15. So sometimes these changes of indices are useful. Okay, we can also sum over things like sets. So here's a sum over x is contained in S of x squared. You have to know what the set S is, but let's say, for example, S equals -2, 5, and 1. So this is saying pick any of the elements in S first to let x be equal to, let's say -2. So this will be -2 squared. And then pick another element in S. I'll just pick the 5, so it'll be +5 squared. Pick another element of S, say 1 plus 1 squared. And those are the only elements in S. So this is 4 plus 25 plus 1 is equal to 30. And we can do this in general. And this is like a for each statement in Bash. Right, we can say for each, and you can specify a variable that takes on all the elements of some set, some collection. And it iterates across each of those elements, setting your variable equal to each element in turn. We can also do algebraic tricks like this. So if we want to sum some function from 5 to 10, we could sum from 1 to 10 and then subtract the sum from 1 to 4. Because if you expand each of these out, the first 4 terms of this sum are going to be canceled when you subtract off the terms of this sum. And it's going to leave you just the terms for I equals 5 up through 10. So that's another way to deal with different indices. And finally, there are infinite sums. We can go from some number up to infinity. We can go from -infinity up to some other number, or we can go from -infinity to infinity. And when you have infinity in the limit of a sum, it means just keep going, right? It's not a number, but whatever number you're at, you want to keep going beyond that. So the classic example of an infinite sum might be sum from I equals 1 to infinity of 1 over 2 to the n. So it's a half plus a quarter plus an eighth plus a 16th plus a 32nd and so on. And if you add those up, you actually end up with just 1. So sometimes, even though you're adding an infinite number of things, you end up with a finite sum, which is pretty cool. It converges to it. It never actually gets to it because you never finish adding things. But we write this meaning that if we were to go all the way to infinity, we would get to 1. There's a more precise way, but then we have to use epsilons and deltas. I don't want to do that to you. All right. We'll stop there. So I want to touch on matrices tomorrow and just kind of remind you of what matrices are about. It's a good example of using summations. And then we're going to start talking about mathematical induction. So that'll be our main topic for the week.